Alright guys, so in this video we're going to start with this study setting. So under frequency domain, put an F, and then for the time dependent we want to set the time, set the range from 0 in the step of 10 to 300 seconds. Alright, and let's go ahead and change. Last time I forgot to change the initial point for temperature is 310.15. Body temperature, make sure you have the correct total power dissipation density on. Last minute check here. Port. Okay. Scatter boundary. Make sure it's frequency domain under EM. User defined F. Okay, that should be good. So now we can compute. So some of the common mistakes is that not putting the correct heat source. So people see there's no temperature rise, and it's like, what's going on? Why is it not working? So make sure you add a heat source in the about heat transfer, and also don't forget to put the frequency domain under this module. Okay, and our simulation should be done. COMSOL takes a lot of your CPU power. So if you notice that it's running like 9% or something, it's pretty interesting. So like in the tutorial online, they suggested we use the log scale to look at the result for the electric field, since it has a logarithmic pattern. It's good. And let's look at the temperature map. We're looking at the point 300 seconds, this FYI. That's a temperature map. You can rotate it and do a bunch of things. You can also save the image snapshot here. Click on this. Let's go ahead and do the integrate the power absorbed in the tissue. So what you do is under derive, right click on derive values and click on integration, surface integration. And what you want to do is select the domain you want to integrate and replace the equation with the heating losses and total power. Also compute volume integral, check here, and under integration setting, compute volume integral, make sure you do that. Integrate. Okay, that's good. This is very closely what they have on the tutorial. The reason why it's a little different because I have like metabolic heating and stuff, so just FYI on that. I want to go in detail of plotting temperature over time. Let's go. I think we have time to do that in this video. Let's go ahead and do that. So under dataset, put cut point, cut point, cut point 2D. Click on that, and we want to look at temperature at a constant z of 0.016, which is at the point of the gap. This gap right here is where you have the largest EM magnitude. The greatest heating comes from here. And we want to do range for our spacing. So we start at say 0.0025, and we'll have a step size of 0.00. Let's do 25 also. And the final point we want is I don't know, 0.0075. Let's see and plot that and see how it looks like. Okay, so that's 3 points. Why don't we do another point? See what happened. Okay, let's plot 4 points. That's good. And then right click on results, and you want to do 1D plot group. What you do is data set, cut point to the all time. Let's go ahead and okay, legend settings here. Right click on plot group and add a point graph. So that's going to plot stuff over time and replace that with the temperature map, a temperature here, and change to degrees Celsius. Under expression, legend, show legends. Great. So you notice the temperature has not reached steady state, so you probably need to heat this longer or lower the power. We shall see later on. So I think this is a good stopping point. Later on, we'll add another module to this, physics. We're going to add the PDE interfaces and general form PD. Let's go ahead and add it, and then we'll finish it in the next video. Alright, so add PDE, and you can label this something like this, or hyperthermia. This is a name, it's not really important. The dependent variable is kind of important. Let's do CEM for, so this is going to be our dependent variable, the cumulative equivalent minute. Alright, so we're good to go. And click on finish. And go ahead and save this for now. Alright, I'll see you in the next video. Thanks for watching. Leave comments, subscribe. Just let me know what you think.